Alrighty. We are going to finish the notes quickly. As a refresher, we've been talking about two new points of concurrency. Let's go to the first one was the orthocenter. Who can remind us where does an orthocenter occur? When?
The point where the three altitudes meet.
Good. She said the points where the three altitudes meet. Remember, an altitude is from a vertice perpendicular to the opposite side. Okay, so if I did that for all three vertices of my triangle, they would intersect at the orthocenter. Good, good, good. The other point we are talking about is the centroid. Who can remind me what that point is? Alejandro?
The point where all the medians meet.
Beautiful. Point where all the medians meet. Median is from the vertex to the midpoint of either side. And that's where our triangle balances. And a special characteristic of the centroid is that the length of the median, if I take the distance from the centroid to like the vertex side, it's always 2/3 the length of that median. Okay, whatever one's on the vertex side. And then on the other side, it's always 1/3 the total distance of the median. So we did a couple example problems like that, and that's where we left off. Okay, so the only one we really have left, and there are some like this on your homework, where you have to graph and find the centroid. So this one's like a word problem, but you're essentially going to do the same thing on your homework with doing this on a coordinate plane. So this example says, an artist is designing a sculpture that balances a triangle on top of a pole. In the artist's design on the coordinate plane, the vertices are located at 1, 4, 3, 0, and 3, 8. What are the coordinates of the point where the artist should place the pole under the triangle so that it will balance? All right. What is the point where my triangle balances? Is that the centroid or the orthocenter? Centroid. Good. Centroid, where the medians intersect. So we need to find the centroid here. Let's go ahead and plot the vertices of my triangle here. Use a straight edge to draw your triangle. 1, 4, 3, 0, and 3, 8. I am going to label these A, B, and C just to help me a little bit when I go to do my math and my work on the other side. But please use a straight edge. Actually, I think I have a ruler on the next slide here. Let's see if I can bring this ruler in over here. So you can use a straight edge. Okay, draw your triangle. This is hard to do up here, but I'm trying my best. Okay, straight edge. A to B. B to C would be a nice straight vertical line. Ooh, that edge didn't work for my straight edge. Okay. And I think it's hard to turn. Okay. A to C. You guys know how to use a straight edge, hopefully. Let's get this ruler out of here. We'll use it on the constructions. So if I need to find the centroid, I need to essentially find the midpoint of at least one of my sides and connect it from like the opposite vertex. So here's my advice to you. That's kind of like our first step here, is you want to find a midpoint of one side. But my advice to make this easier on yourself, you want to find one whose median makes a vertical or horizontal line. I will kind of explain why that's easier as we go through the process here. But it's going to save you a lot of steps. And we don't actually have to tackle it the way like that we did with the ortho center, where we actually had to like find the equations and like set them equal to each other. We can do it because of the characteristics with the median being like 2/3 from the vertex side. So we'll be able to locate it another way. And the easiest way to do it is if your median is vertical or horizontal. Okay, so everybody look at my vertex A. Do you agree that if I were to draw a median from vertex A, so that means from the vertex to the midpoint of this side, that would make a horizontal line,
Yes.
right? And I know we can all visualize what the midpoint of BC is, but in case it's not a nice horizontal vertical line, let's just refresh how we'd find the midpoint of BC with our midpoint formula, which is average the x-coordinates. So let's see, 3 plus 3 over 2. Average the y-coordinates, 0 plus 8 over 2. So we'd get the ordered pair. Let's see, 6 divided by 2 is 3. 8 divided by 2 is 4. 3, 4. That makes sense. I'm going to call that point D, or midpoint there, D. So to draw in your median, I already did this, but once you find the midpoint, take your straight edge, connect the vertex opposite that side, and connect it to the midpoint. And if you want to do this to like notate to yourself that that's the midpoint, you can. But there's our median. Now, as I mentioned, we actually don't need to find another median and look for their intersection because of the special characteristics of the centroid and where it's located on each median. We know, I write this down, the centroid is 2/3 the distance of the median on the vertex side. Now, the reason why we want a median that's a horizontal or vertical line, and in this case it's horizontal, is that's really easy to calculate the length or the distance of this median. We don't have to use distance formula. What's the length of that median? What's that distance? 2, right? So that median there is 2 units. So I know that my centroid is located 2/3 of that distance on the vertex side. So from point A, 2/3 of the way here, you guys know what 2/3 of 2 is? You can think of it as 4/3 or 1 1/3. And visually this makes sense. 1 1/3 would be about here. That's where my centroid's located. 2/3 of that distance. Okay? Now we do have to find the actual coordinates of this point of our centroid. So looking at this point here, what is the y value, obviously, of this point? 4, right? The y value is definitely 4 because it's lying on this horizontal line. So we know this is 4. Okay, careful with the x-coordinate. The x-coordinate is not 1 1/3. Right? Think of plotting this point. We start here at the origin. So I would go 2 1/3. 4, so this would be 2 1/3. Or you can do improper fractions if you want. But that's where that centroid would be. A lot easier than that problem we did with the ortho center where we actually had to find the equations of the altitudes and figure out where they intersect. You could do it that way. You could find the equation of 2 medians and set them equal to each other, but use that special property of centroids to like save yourself time. And again, you don't have to choose this median. If there isn't one that's a vertical or horizontal line, you're going to have to pick one that's not a perfectly horizontal or vertical, and then you just have to use like the distance formula to figure out the length of the median, okay, and figure out what 2/3 of that is. All right, that was the last example problem we needed to do. The only thing left in the notes, we will do a couple constructions with centroids and orthocenters, but first, I put this chart in your note because I kind of like this. It's a good like graphic organizer of every point of concurrency that we talked about so far. Okay? So it's a review from 5.1 and then our new lesson 5.2, which reminds me you guys have a quiz coming up, so we got to talk about that. Don't let me forget. All right, so special segments and points in our triangle. One of our special segments, the very first thing to talk about, are perpendicular bisectors. Okay? Notice how they're different than altitudes. Altitudes go from a vertex to the opposite side. A perpendicular bisector could be anywhere within the triangle. It doesn't have to pass through the vertex. It just has to be perpendicular to the side and bisects it, meaning it passes through the midpoint. Okay, so we talked about, like, with those ones, their point of concurrency can be inside the triangle, outside, or even on the hypotenuse if it's a right triangle. Remember that? All right, so if I take the perpendicular bisector of each side, I'm going to highlight them in green here. This is the perpendicular bisector of AC. This is the perpendicular bisector of BC. This is the perpendicular bisector of AB. Okay, it's splitting all these sides in half. Ignore those lines from the vertices for now. So where those perpendicular bisectors intersect, do you guys remember what we call that?
Cosine.
What? Circumcenter. Did someone say cosine?
No, I said cosine.
Oh, that's a new one. Okay. That was the very first one we talked about before Christmas break. Here's their special characteristic. So here's what they're showing you in the picture. From the circumcenter to each vertice, these are all equidistant. So I'll use a squiggly line. Those are all the same distance. That's their special property. All right. The other one we talked about before Christmas break was where all the angle bisectors intersect. So here they're showing you what an angle bisector is. Over here, I'm going to highlight this in green. This is the angle bisector of angle A, angle bisector of B, angle bisector of C. Their common point of intersection, these ones always lie inside the triangle. Remember what these are called? In-center. Good. Their special characteristics is that they're equidistant from each side of the triangle. Okay, don't let their picture throw you off here. If you're looking at there and you see right angles, you're like, oh wait, are they showing me perpendicular bisectors, altitudes? They're showing you that the shortest distance from a point to each side would be the perpendicular distance. So if we're looking at the shortest distance to each side, those are all the same distance, or equidistance. That's their special property. Okay. So in green, I'm kind of highlighting where that point occurs with what type of special segment. And then in blue, I'm doing kind of like the special property of each. Our two new ones from 5.2, where our medians intersect. So medians and altitudes are always like from a vertex to the opposite side. A median is from the vertex to the midpoint of each side. From vertex to the midpoint. Vertex to midpoint. Those connect at the centroid. That's the one where our triangle balances. Their special property is that on the vertex side, so if I'm just looking at the median right here, BD, on this vertex side from B to R, to the centroid is 2/3 the distance of that median, the entire median, and this is 1/3 the distance of the entire median. That's their special characteristic. And then lastly, altitude. So that's from the vertex perpendicular to the other side. That can also lie outside the triangle. That's our orthocenter. So here they're showing you each altitude. So the altitude for A would be from the vertex A and then perpendicular to the other side. From vertex B, perpendicular to the other side. From vertex C, perpendicular to the other side. Where they intersect, that's the orthocenter. There's no really special characteristic for the orthocenter. There's no like, oh, it's equidistant from here to here. These can lie outside the triangle. Okay, I mentioned yesterday that you guys did problems like this where I said, that's a poor drawing. Let me try that again. Where I gave you like this point P. And I'm like, hey, what's the shortest distance from this point to line AB, and you always found the line straight down, or the perpendicular distance, right? That's really an altitude. So obviously from our example there, like in an obtuse triangle, it could lie outside the orthocenter. Okay, just a couple constructions to do here. All you need is a straight edge. Whoops. If you don't have one handy, you can grab one back there. Otherwise, folks, we're just gonna keep this pretty basic. We're just gonna kind of like estimate this. How did I get that ruler to turn? Oh, let's see here. Come on. Okay. It was working last hour, of course. There we go. The first one we're going to do is the centroid, which that's my medians. So we're going to measure the midpoint of each side. I'm going to use centimeters just because I think centimeters are a little bit easier to work with when I'm finding like half the distance. So let me just make my ruler. Okay. So if I measure this side, and obviously like you can see here that I just changed the numbers based on how big my ruler is. So I'm just going to kind of estimate my midpoint. You can do the same thing. You can tell me exactly what this is. My midpoint here would be right here at 4 centimeters. If that whole segment's 8 centimeters. I don't know if it's actually 8 centimeters. I'm just using this ruler. If you don't have a straight edge, just kind of guess where you think that midpoint would be. What I do want you to use is a straight edge. So I want you to take your straight edge and connect the opposite vertex to the midpoint. Okay, so let me get my ruler here. That's looking pretty good. There we go. There's one median of my top vertex. So now we're going to do the same for the other two sides. Okay, let me get out my ruler here. Let me measure this next side. This one's a little over, looks like 8.2 centimeters. I'll just do about 4.1 about there. This is just rough, not exact. Okay, take your straight edge, connect. This ruler is not the most fun thing to do on this board. Connect from the opposite vertex to the midpoint. There's that median. Okie-doke. Last side here. Okay. 1, 2, 3, 4, 5, 6. That looks like it's about 6.8. So 3.4. About there would be the midpoint. Take my straight edge. Connect. From the midpoint to the opposite vertex. Okay, obviously, I feel like my straight edge doesn't work for some of the sides. The more accurate you do this, the more accurate your centroid is going to be here. But they should all cross at a point. If they don't cross exactly, just make your point a little bit bigger. But that right there, folks, that'd be our centroid. Maybe I would add in some markings here that it passes through like the midpoint of each of these sides. To remind yourself, that's what a centroid is. Okay, that's how you construct a centroid. Now, obviously, like on a coordinate plane, we can be more exact because we can like find those exact midpoints, all that good stuff. Next one we're going to do is our orthocenter. So you do want to use a straight edge for this one as well. So it says, use a ruler on something that has a right angle. Draw a line through the vertex that's perpendicular to the opposite side, aka we're just going to draw all the altitudes of each vertex. Let me make my ruler a little bit smaller here. Okay, so starting with this bottom base of my triangle, which is a horizontal line. Obviously, perpendicular to that would be a vertical line. So you're going to take your straight edge straight up and down. And we're going to connect the vertex to that base, and there would be that altitude. So it says, use something that forms a right angle. We're going to use our ruler. Okay, I'm going to do this next side right here. So I kind of want to adjust my ruler until I find something that looks like a right angle. Obviously, this is a really acute angle. See what I'm looking at? That's really obtuse. So that looks pretty good. So it needs to pass through the vertex, perpendicular. I feel like I could do a little bit better, actually. Probably more like that. Through the vertex, perpendicular to the other side. There would be that altitude. And then my last side there, I need to put my ruler perpendicular. Something like that. So from the vertex, perpendicular, there would be that altitude. Okay, obviously we're kind of doing a lot of approximation here with the right angles. So you can see then maybe isn't exact, but that point right there, that'd be my orthocenter. Draw in right angle so you know that we found the altitudes there. If yours don't cross at a point, you probably did something wrong. But that's it for the note packet, unless we have questions. All right, ready to get to work?